A large solar power plant is set to reduce CO2 emissions by 136,000 tons per year. The project reflects a global trend. Floating solar parks could become the next big innovation in the green energy revolution. It uses the sun's rays on lakes, seas, and reservoirs. The electricity has now been connected to the largest such installation of its kind. The facility, developed by Hexa Renewables, has been launched off the west coast of Taiwan. Part of a global trend. The floating solar park covers a massive 347 hectares, which is more than 400 football fields in size. With a capacity of around 440 megawatts, it can now provide electricity to 74,000 households through solar panels floating on the ocean's surface. The solar cells are connected to the mainland via extremely protected underwater cables that transfer the generated electricity to the grid on land. Just like any other solar panels, they generate a floating current when hit by the sun's energy-rich light particles, called photons. This causes electrons to travel between the different layers of the individual solar cells, and this cycle ultimately results in electricity that can be drawn from an outlet. Solar cells are still growing. The technology behind solar cells has now developed to the point where solar power can compete with all other energy sources. With new generations of solar panels, we will be able to use even more and cheaper solar energy. First generation, silicon. Behind the breakthrough, experts refer to the well-known crystalline silicon solar panels as the first generation. The advantage is that they are efficient and long-lasting. The downside is that they are inflexible and require large amounts of energy to manufacture. Second generation, new materials provide flexibility. In the second generation, there are thin-film solar cells made from various materials. The film is flexible and can be produced quickly, but the downside is that it is often less efficient and has poorer durability compared to silicon-based cells. Third generation, organic solar cells, become cheaper. Third-generation solar cells consist of both inorganic and organic materials. The organic solar cells are often designed as a thin, light foil that can be applied anywhere, is cheap, and has the potential to be highly efficient. The extensive facility off Taiwan consists of over 100 million small solar cells, which are reportedly capable of reducing CO2 emissions by 136 tons per year, according to Hexa Renewables. For the same reason, offshore solar energy is expected to play a central role in future energy supply. Wind farms have already utilized open sea areas to reduce pressure on land areas, but floating solar parks are seen as a promising alternative, especially since 71% of the Earth's surface is covered by water. The available space makes it possible to install large facilities in areas with abundant sunlight. The stronger the light and the more hours of sunlight per day, the more electricity is produced. One notable disadvantage of offshore solar cells is that the salty air and the foam from the waves can severely damage the solar panels. Solar cells are also moving into space. Solar cells are set to play a crucial role in the green transition, but there is one problem: darkness. That's why the European Space Agency, ESA, is now sending solar cells into space, where the sun always shines, and wirelessly beaming green electricity to Earth. The International Space Station is our greatest engineering achievement in space so far, but according to ESA, we need to think bigger, much bigger. ESA researchers are working on quenching Earth's insatiable thirst for green electricity by placing giant solar power stations in space. These stations will orbit 36,000 kilometers above the Earth and supply 1 million European homes. It may sound like a crazy idea to build a 15-square-kilometer solar power park in space, but we already have the technology needed. Plus, analysis shows that the benefits in terms of clean energy will be so great that they will outweigh the economic disadvantages of construction. That being said, the project, named Solaris, is no small feat. The engineering challenges are immense. How will a construction the size of 2,000 football fields unfold in space? And how will the electricity be transported back to Earth? To find the answers, ESA is reviving a 55-year-old idea from the drawing board. The atmosphere reflects the sunlight. The idea of placing solar panels in space is not new. In 1968, American-Czech space engineer Peter E. Glaser presented a concept for using satellites to harvest solar energy, which would then be transmitted to Earth. Gleiser discovered that there are significant advantages to moving solar power installations out of Earth's atmosphere, despite the challenges of installation and maintenance. First and foremost, Earth's atmosphere reflects a large portion of the sunlight back into space. Around 30% of the light never reaches the traditional solar panels on the Earth's surface. At the same time, fog and clouds can cause a phenomenon called diffusion, which spreads and bends the direct sunlight. As a result, sunlight is about 10 times more intense at the top of the atmosphere than near Earth's surface. The farther solar cells are from Earth, the more effectively they can harvest solar energy. Lastly, solar cells in space could also solve the biggest problem of terrestrial solar cells: darkness. In a so-called geostationary orbit where the solar park follows the same point on Earth, the solar panels at 36,000 kilometers will be hit by sunlight 99% of the time. The large amount of energy will then be converted into electricity and sent to Earth. This is not without challenges, as electricity cannot be transported via the power grid but instead must be transferred wirelessly. Peter E. Gleiser had even proposed how this wireless transfer could work. He suggested using electromagnetic waves to transport the electricity. Electricity converted into microwaves. The electrons created when sunlight hits the solar cells cannot be sent to Earth in their original form, but if they are converted into microwaves, the energy can be transmitted over thousands of kilometers. The principle is the same as in a microwave oven, where electrons are passed through a magnetron and converted into microwaves. These then transmitted through an antenna and sent toward Earth. Solar energy transmitted wirelessly to Earth. The massive solar power park will be built high above the atmosphere. There, the solar panels will convert solar energy into electricity, which will then be converted into microwaves. Solar rays are captured 24/7. The solar park will be placed 36,000 kilometers above Earth, where it will have uninterrupted access to sunlight, almost 24/7. The orbit ensures that the solar park always follows the same point on Earth where the receiving station will be located. Sunlight converted to microwaves. The solar cells produce electricity, which is then passed through a magnetron, the same type used in microwave ovens. The magnetron creates a magnetic field, and when the electrons from the solar energy enter the field, they are converted into microwaves. Solar energy sent to Earth. With the help of an antenna, the microwaves are transmitted toward a receiving station on Earth. The microwaves are sent with low energy, meaning they are not harmful to animals or humans that may move through the beam's field. Microwaves converted to electricity. On Earth, a receiving station, covering 71 square kilometers, will be equipped with special antennas called rectennas, which convert the microwaves back into electricity, which will then be sent to consumers through the power grid. The advantage of microwaves is that with their short wavelengths, from 1 meter to 1 millimeter, they pass almost unobstructed through Earth's atmosphere, without being slowed down by the atmosphere's molecules. No one has yet succeeded in sending microwaves over such long distances, but since 2020, a test involving solar cells on a spaceplane has successfully converted solar energy into microwaves. The results of the test are expected to be released soon. On Earth, the microwaves are received by special antennas, which convert the electromagnetic energy in the microwaves into direct current. The receiving station will cover an area of 71 square kilometers. Another possibility is to convert the electricity from space-based solar cells into laser light, which will be directed straight at a solar park on Earth, where the solar cells can convert the laser light back into electricity. Regardless of the method chosen, the biggest challenge for space-based solar cells is the energy loss that occurs when electricity is converted into microwaves and then back again. Space solar cells will also be a supplement to other green energy sources, as calculations show that it will require 20 to 25 space-based solar power stations to meet 10% of the EU's estimated electricity needs by 2050. Solar cells folded like origami. Although the entire concept may sound like science fiction, ESA emphasizes that the technical solutions for space-based solar panels already exist. The biggest challenge will therefore be constructing a structure in space on a scale never before seen. Today, the largest engineering feat in space is the International Space Station, ISS, which, including its solar panels, is about the size of a football field, around 7,100 square meters. In comparison, a space-based solar park would have an area of more than 15 square kilometers, more than 2,000 times as large. Studies suggest the project will take 5 to 10 years to develop, while the robots needed to assemble the solar park in orbit around Earth will take another 10 to 20 years to build. The robots will either be remotely controlled from Earth or assemble the construction's approximately 2 million components on their own, including solar panels, sensors, motors, and microwave transmitters, competing with nuclear power. To make it easier to transport the many components into space, researchers at Caltech in the US are developing a new type of ultra-thin, foldable solar panels. The advanced solar film delivers 50 to 100 times more power per kilogram compared to traditional solar panels and is mounted on a thin, strong composite material. The third layer in the millimeter-thin construction consists of antennas mounted directly on the back. Solar cells will fold up. A 15 square kilometer solar park occupies an extremely large area. To minimize rocket launches, researchers at Caltech have developed an ultra-thin roll of carbon fiber coated with solar film. A motor in the center of the roll unspools the film to full size once the structure is in orbit and ready to absorb sunlight. In space, foldable solar cells will be practical because they can be packed very tightly and loaded onto a single rocket, after which they unfold once in orbit. As with other energy technologies, the success or failure of space-based solar energy will ultimately depend on the cost of producing a kilowatt-hour for electricity customers. Although building the solar power stations is expensive, the estimated cost for the first station is 13 billion euros just for construction. The price will decrease over time. Since the stations have direct access to sunlight 24/7, the price per kilowatt-hour will eventually be able to compete with both nuclear power and terrestrial solar and wind energy. Thus, Peter E. Glazer's 55-year-old idea is on the verge of becoming a reality. Unfortunately, the inventor will not live to see it come to fruition. Glaser passed away in 2014 at the age of 90. If you found this information interesting, please consider clicking like and subscribe for more videos like this. We sincerely thank you for staying until the end. We want to wish you a fantastic day.